So today we are going to derive a very important equation, that is Bragg's law. So what is this Bragg's law and how it is important in crystals? So we already discussed that crystals, they are 7 types. As per the classification of Bragg, there are 7 types of crystals, and these crystals are classified based on their parameters, that is the dimensions of unit cells and the angles that the planes make with their axis, that is ABC values and alpha, beta, gamma values. Then, how do we identify the type of the crystal? How can we say that this crystal is trigonal, this is orthorhombic, this is cubic, like that? Then the procedure is, first we have to find out the Miller indices, as we discussed in the previous class. Miller indices are the reciprocals of the intercepts of the planes, crystal planes on the 3 axes. We know that in Miller indices are denoted by HKL values, and by finding the Miller indices, and we have different sets of Miller indices also, because we can find different sets of the planes, crystal planes, lattice planes in the crystal lattice, as we discussed in the previous class, X, Y, Y, Z, ZX and XYZ planes. So obviously we have different sets of Miller indices. And I also explained that Miller indices are very significant coordinates, and they do not represent a single plane. Miller indices represent set of parallel planes, and if you identify the Miller indices, we can study the characteristics of the set of those parallel planes. So, how to calculate Miller indices and how to identify the shape of the crystal, structure of the crystal. For that, Bragg, he has derived an equation to identify the interplanar distance. He used the phenomenon of diffraction. So diffraction is the phenomenon of, actually we studied in light. Light bends at the sharp edge. This is called diffraction. And after diffracting through the sharp edge, the light produces diffraction pattern on the screen. So this is the ordinary light. Ordinary light, visible light, whose range is from violet to red. If we use ordinary light to pass through the crystal, it means to identify the crystal structure, we have to pass the radiation through the crystal, and then so that radiation diffracts through the crystal, and we have to study the diffraction pattern there. So crystal, how we for that we have to see the crystal structure, crystal planes here. So we have different planes in the crystal structure. So I will denote the planes like this. So these are the different planes here, and these planes are parallel to each other. So when these planes are identified, then here we have the atoms which are located in these planes. So these atoms are denoted by, we denote with the circles here. So these are the atoms. So we know that in the lattice structure, the atoms are arranged in rows and column wise to get a shape, particular shape. So these are the planes and we have the distance between two planes. Distance between the two planes is interplanar distance. So this is the distance between two planes. So this distance we denote with d. So this distance is denoted by d, and this interplanar distance is very important. And we have to identify this interplanar distance here. So this is the distance d. So as you know, the atoms inside the substance, that too solid. So we are discussing the solid crystals only. So almost all the crystalline structures are available in solid state. So in solid substances, the atoms are closely packed and the distance between the two atoms is uh, very small. So for that, the gap between the two atoms. So this is the gap between the two atoms. That is the interatomic distance. This distance is very small. And to study the shape or the structure of the crystal, so we use this as a diffraction grating. A grating is opaque substance on which sharp lines, sharp slits are made. So sharp slits are transparent and distance between the two slits is opaque, and when light passes through the grating, sharp slits, sharp edge, diffraction takes place and we can see the diffraction phenomenon. Similarly, if you take this crystal, this is the crystal. So in this crystal, there are atoms here. Distance between the two atoms, this acts as transparent to the radiation. I call radiation, whether it may be light or any other radiation, we will discuss very soon. And this atom acts as opaque. Opaque means it does not allow the radiation to pass through this one. It just scatters the radiation. So here, this is the crystal lattice. And we have the lattice planes. So these are the lattice planes, parallel lines. This crystal lattice here, we have the atoms which are arranged and which are located in the parallel set of the planes. It acts as diffraction grating. So first we have to identify which is opaque and which is transparent. Every atom acts as an opaque point, and distance between the two atoms is a transparent here. Now, so how to identify this diffraction grating, this crystal lattice as diffraction grating we are using, and which type of radiation is to be used to identify the structure to produce the diffraction pattern. And this is the next question, next point. Suppose if you use ordinary light, like a visible light from violet to red, which varies the wavelength from 3000 Armstrong units to 7000 Armstrong units. This radiation, visible light, having large wavelength, it means it does not suit to pass through the crystal lattice. The reason is distance between these two atoms inside the crystal is very small, short, comparing with the visible light. So when you compare with the visible light, this distance is very short. So this distance, which is very short, does not suit to ordinary light. Then what to be used here? We have to use a radiation which has very small wavelength, which has very shorter wavelength. Then Bragg used X-rays. So X-rays, they have very short wavelength. So X-rays are also radiations having short wavelength. This is the reason why Bragg used X-rays to identify the crystal structure. So instead of using ordinary light, if you use X-rays, X-rays are powerful radiation with very short wavelength. They can penetrate through the crystal lattice. Okay. If you use ordinary light cannot penetrate through crystal lattice, even though it is transparent. Just it passes through the substance if it is transparent, but it could not penetrate through the lattice of the given crystal. It cannot diffract through the crystal lattice. But X-rays are powerful radiation with very short wavelength, and then if you use this radiation, it can penetrate through the crystal lattice. Then what's the next step? We have to study the penetration of X-rays through the crystal lattice, how it is scattered by the atoms here. So here I am using a radiation, so which is incidenting on a crystal lattice. So a radiation means a beam of particles, beam of photons, a beam. So a beam comes and so it incidents directly on the atom. As atom is an opaque point, so atom acts as an opaque material, opaque. Then it is scattered by this atom. So this is the direction of incident X-ray. So this is X-ray. And then it is scattered. So here we have to identify what is the angle of incidence. For that, I will draw a line, perpendicular line. So this is the perpendicular line to the crystal lattice, and here we have the angle of incidence. So this is the angle of incidence. We denote this with I. Generally we denote with I. Now I represent this angle of incidence with theta. So I represent with theta is the angle of incidence. And then later, if this X-ray is scattered by the atom, then what is the direction of the X-ray? So the X-ray is scattered in this direction. This is the scattered X-ray. So this is scattered X-ray which is diffracted here, and this is the direction of the scattered X-ray. Again, this angle is theta. Next, we have another plane just below this first plane. These are the adjacent parallel planes here. Now I'll consider another beam which strikes the atom exactly below that atom here. This is another one. And then this is the direction of the second beam, which is incidenting on the second plane, that is a plane which is exactly below the first one. And again it is scattered by this X-ray, by this atom in this direction. So this is the direction of the X-ray. and then direction of this scattered light is in the same direction here. Okay, so I will represent this point angle of incidence for the first one. So this one I'll represent with the O, and this point is I'll represent with the O dash. Then these two scattered X-rays, so I will do this one with a 1 and this is 2. These two scattered rays diffract with each other and they will produce diffraction pattern. By studying the diffraction pattern, we can identify how many sets of Miller indices are there. So that is another topic here. I'll explain in the next lesson. So meanwhile, for this lesson, I'm going to derive the condition for maximum intensity during this diffraction. In terms of interplanar distance, this is interplanar distance, and in terms of theta, and in terms of wavelength here. So now here X-rays have wavelength. So I will denote the wavelength of X-ray as lambda. So wavelength of X-ray is here lambda. Wavelength, and it is a very short wavelength. Now, these two are the scattered X-rays. To find the condition for maximum intensity of diffraction, if you keep the screen here, you can observe the diffraction pattern. So to identify the diffraction pattern or the maximum intensity, we have to calculate path difference between these two, 1 and 2. So we have two scattered X-rays. There is a path difference between 1 and 2. What is that for that? So for that, here I will take, I will draw a normal here. So this is the normal, which is drawn onto the second one. And this is also another normal here. And if you look at this one, this one. So I will denote this two normals here with the one is M and another is with N. If you look at this, before this OM, this is OM line. Before this OM, these two lines travel, or these two X-rays travel equal distance. So before this line, they have the equal path, and beyond ON, this is ON. Again, scattered X-rays travel equal distance, they have equal path. I repeat once again, we have to calculate the path difference between two scattered X-rays. For that, I have drawn a normal here, OM, one normal, and another normal from point O onto the second scattered ray, ON. So for finding the path difference between these two, we observe that the distance traveled by two incident X-rays. These two are the incident X-rays, and distance is equal, so their path is equal. And what about the scattered X-rays? Beyond this line ON, perpendicular line ON, these two scattered X-rays travel equal distance. Then what's the path difference between these two X-rays. Here we can observe that the second X-ray, so after penetrating through the crystal lattice, when it strikes the point atom here at the point O dash, it travels an extra distance OM. OM is the extra distance traveled by the incident light. Next, coming to the scattered X-ray, the second X-ray, again here it travels an extra distance ON inside the crystal lattice. So, the path difference between these two is delta, we can write it as, which is equals to ON plus OM. This is the path difference. So this is the path difference here. So path difference equals to ON plus OM. We have to find out this. We have to find out this path difference. So how much path difference is obtained by this ray? For that, I will draw again a line here, which is equals to D. So this line, this is equals to D, interplanar distance between these two parallel lines, adjacent lines. And again here we have this angle theta, and this is also theta here. So this is theta angle here, and we have to go through that one. This is angle theta and this is also angle theta. And this is opposite side of the triangle, right angle triangle OM O dash, and this is ON O dash is a right angle triangle here. So for this right angle triangle, the hypotenuse is O dash D. So here I will write that one, O dash equals to D, interplanar distance, and then here OM and ON both are equal here. So OM equals to ON, and path difference will be here. So path difference, we have to calculate that one. This will be OM plus ON, and this is equal to here 2 OM. We can write like this. So both are equal, OM and ON. So I'll write OM plus ON equals to 2 OM. If you calculate OM, then you can substitute this one, path difference. Now here I am going to calculate here, right angle triangle here. OM is the opposite. So OM this is opposite side and O dash, which is hypotenuse. Then we can take sine theta. So I will take sine theta. Sine theta value is taken here. So sine theta, I will write like this. So which is equal to here, this is opposite side divided by hypotenuse. So which is equals to opposite side divided by hypotenuse. And then this is sine theta value. This is equals to opposite side means here we have OM. So this equals to OM divided by hypotenuse is D. So we want OM, then OM equals to D sin theta. So OM equals to D sin theta. So this is the path difference for one ray. And then we substitute this OM value in this equation. That is the path difference equals to 2 OM. So then we will have path difference equals to 2 OM equals to 2D sin theta. So this is the path difference. So this path difference here, now we calculate in terms of lambda. Lambda is the wavelength. So for a maximum intensity, path difference must be equal to here n lambda. So path difference must be equal to n order of the diffraction fringe, and this is equals to n lambda here. So this n lambda path difference, and then these two are equated. This is path difference equals to 2D sin theta, and here path difference equals to n lambda. So 2D sin theta equals to n lambda. This is the required equation for path difference. This is called Bragg's law. So 2D sin theta equals to n lambda is the Bragg's equation here. So this equation is used to find out the interplanar distance, and by studying the pattern of the diffraction we can find out how many different sets are there by just observing different sets of Miller indices. Here theta is the angle of incidence, d interplanar distance, lambda is the wavelength, n is the order of the fringe. So this is about Bragg's law. Next lesson is about Bragg's spectrometer. Using that spectrometer, how to identify the crystal structure. This is the next topic.